So it's a great pleasure to be here. I want to thank the organizers for inviting me. Obviously, I didn't expect such a diversity of topics. So if I'm confusing you or if you have any questions, feel free to ask as I go along. So I'm going to talk about basically nanoscience, mainly plasmonic science, interaction of light with plasmonic materials. But on top of that, there will be another layer, which is chemistry. So on top of the interaction of light with these plasmonic nanostructures, I'm going to talk about how these things can drive chemical transformations. So I'm going to start by just talking a little bit about chemical transformations of metals in very broad terms. I'm going to talk about differences between extended metal surfaces, for example, a single crystal of a metal, and metal nanoparticles in the way they interact with light. I'm going to particularly kind of focus on these localized surface plasmon resonance. I'm going to discuss the physical characteristics of this localized surface plasmon resonance, and I'm going to pivot to chemistry and ask a question whether these materials can drive chemical reactions on their surfaces and what are the underlying mechanisms. And in particular, I'm going to focus specifically on this charge transfer from one material to another material in these conditions of localized surface plasmon resonance. So when we think about chemical reactions on surfaces, and these chemical reactions on surfaces drive really a large fraction of our economy through catalysis, we think about thermal processes mainly. And in this process, you have I'm going to try to, let's see how this will work now. Probably it's not going to work very well. So here I show a molecule of oxygen adsorbed on a silver surface. And as you see, when this molecule is absorbed, it does not, you don't activate at room temperature this oxygen-oxygen bond. The reason is because you have this anti-bonding oxygen-oxygen state, which is not populated. So if you want to activate this in a thermal process, you would heat this nanoparticle. Your phonon mode of the nanoparticle would couple with the vibrational mode of this oxygen. You start stretching this oxygen-oxygen bond. This anti-bonding state would sink below the Fermi level. You would populate that anti-bonding state. You would go over something that's called transition state, and you would dissociate this oxygen and form atomic oxygen. Same process can take place in an alternative mechanism where you have a way of somehow taking an electron out of this nanoparticle and depositing it selectively into this. Yeah, I definitely cannot work with this. So depositing it into this oxygen-oxygen anti-bonding orbital. In this process, you go to this charged state. You're creating transient negative ion, but basically doing the same thing. You're putting an electron in this anti-bonding state, and now you introduce forces on these oxygen atoms, and these oxygen atoms are now starting to move away from each other, and you're exchanging that electronic energy for vibrational energy, and you can induce chemical transformation that way. Now, the difference here is that you actually can selectively put that energy in a particular chemical bond, and you can selectively activate that chemical bond without heating the entire nanoparticle. So, well, there have been a number of really careful experiments performed, kind of shedding light on this mechanism. So I show work of Gerhard Erl here and some of his co-workers, in which they show that if you basically run a thermal reaction where you have a ruthenium surface and you deposit carbon monoxide and oxygen on a ruthenium surface, and you thermally heat that surface, you basically have a desorption of CO that takes place before oxygen desorbs, and you basically have no reaction. You don't get CO2. You get CO coming off and then oxygen coming off. On the other hand, if you shine a high-intensity laser on the same surface, prepared the same way, you actually get CO2 formed. And what they proposed through a series of calculations and experimental studies is that basically when you shine laser, you create these energetic electrons in the ruthenium surface, and these energetic electrons basically excite your oxygen. You create this excited form of oxygen, and this excited form of oxygen reacts with CO to form CO2 before CO would desorb. So kind of the main curiosity driving kind of discovery of these experiments is that selectivity of these thermal processes, meaning a process that takes place when you heat the surface of the material, and the selectivity of these charge-driven processes, basically light-induced processes, can be very different. So this was a very interesting discovery. However, the problem is that there's really important practical limitation here. And the practical limitation is that you have to have a very high intensity laser to be able to induce the formation of these energetic electrons at the surface of these nanoparticles, or surface of the metal single crystal in these particular experiments. And the main reason why you need this high intensity light is that you reflect a large fraction of your light, but also the light that goes into the surface and creates, or into the metal and creates these electron-hole pairs. These electron-hole pairs are created far away from the surface. And before they can bubble to the surface and activate these chemical bonds on the surface, their energy is lost through the collision with other electrons and the phonon bonds. So you essentially end up heating the surface before you can selectively or efficiently move these electrons all the way to the surface to excite chemical transformations. So now when we come to the concept of metal nanoparticle compared to this extended metal surface, there's a couple of differences. First, obviously, reflection is different, but very important difference is that there's higher ratio of surface to bulk electronic states. So what this means is that if you have these electronic excitations, if you have a large surface area compared to volume, you're going to push these electronic excitations closer to the surface. Another very important difference is that for some of these nanoparticles can support something that's called localized surface plasmon resonance. And this localized surface plasmon resonance is basically a condition in which you have a natural oscillation of this electron cloud in the nanoparticle, and that electron cloud is interacting with the electric field of a phonon that's kind of hitting that nanoparticle. When they're in sync, you get a resonant condition. So what it essentially means is that you can put lots of energy in your nanoparticle, and you can put them in these surface plasmon resonance states. So for example, nanoparticles of silver, gold, and copper exhibit this surface plasmon resonance at the conditions that are consistent with UV visible light, basically with solar applications. So if you have solar light, you can excite this surface plasmon resonance on silver, gold, and copper. And I show here an extinction spectrum for a collection of silver, gold, and copper particle as a function of wavelength. And you see this extinction, which is taking place under these wavelengths for these nanoparticles. Major characteristic of this surface plasmon resonance condition is that you're actually concentrated the light of that, the energy of that light that's interacting with this system at the surface of the nanoparticle. So here I show now intensity of electric field associated with a combination of two silver nanoparticles, so two cubes of silver positioned 45 degrees with respect to each other as they're interacting with light. And you can see that this electric field is dramatically enhanced compared to the field of incoming light. So for all intents and purposes, you are localizing the energy of that light that's hitting this dimer of silver nanoparticles at the surface of the nanoparticles, and particularly between these nanoparticles. You see that these enhancements are anywhere in field intensity, are anywhere between 10 to the 3, 10 to the 4, all the way to 10 to the 6 compared to the incoming energy of photons that are hitting this system of two nanoparticles. So this situation is actually fundamentally different than an extended silver system. So here I show, again, the same collection of two silver nanoparticles. We are computing the value of that electric field. And here we have an extended silver bulk, basically a single crystal of silver under the same conditions. And you see that there's no enhancement in electric field. So for all intents and purposes, I said earlier, the light is really concentrated at the surface, or light energy is concentrated at the surface of these nanoparticles of silver under these conditions. So now the question is, how does this energy of light get dissipated? Well, if you have no chemically active environment present in this system, this energy can get dissipated by the excitation of energetic states or electrons and holes in this nanoparticles. So here you can get absorption process basically, and this absorption process dominates for a smaller nanoparticles of silver, 10 nanometers or less. Or you can have a radiative scattering, where you have a scattering of these photons in kind of all directions as they are moved away from this hot spot, or for this energetic from the system of these nanoparticles. The question that we had when we started in this field is really going back to that early study. So now if we are concentrating energy of this electric field or energy of this light at the surface of the nanoparticle, And if we can induce these electronic excitations at the surface under the influence of this energy, of this electric field, is it possible then under reaction condition, for example, under oxidation condition, to use these electrons and to scatter them through this anti-bonding orbital of oxygen, and in this process induce dissociation of oxygen with this light, as opposed with the thermal pressure, thermal heating that I discussed before. So the concept would be here that you have an electron that's formed in this system, and then somehow this electron finds its way through this anti-bonding orbital, and in that process it dissociates this molecular oxygen, forming atomic oxygen, and then you can use that atomic oxygen, for example, to drive oxidation reactions. So this is the first experiment that we performed. So we deposited silver nanoparticles, very small concentration of silver, on alumina support. And we basically design a reactor that looks like this. We pack this catalyst into basically a reactor. We have a light that we can funnel into the reactor, and we have an inlet. We're bringing a stream of ethylene and oxygen. We're going to follow the oxidation of ethylene as a probe reaction, and they're going to monitoring what's coming out of this system. And these are basically the first results that we obtain here. So here you see a mass spec signal of ethylene coming in. As you turn the light off, you see instantaneous oxidation. So this is now, if I send an inert through this system, I'd get exactly the same, a pulse of an inert gas, I'd get exactly the same spectrum. So there's no really time delay that we can measure. So what you can see here is you start ethylene and oxygen, you have certain thermal process going on, you shine a solar intensity light on this system, and the reaction rate spikes quite dramatically. You turn the light off, the reaction rate goes down. And again, this is an oxidation reaction, so you can think of this as a steady state process that's monitoring the rate of oxygen dissociation. And you can think of this ethylene as just a molecule that's coming in and picking that oxygen off the surface, allowing you to do steady state chemistry. So when you see these kind of results where you're really shining light on a metal surface and you're seeing, and this is a low intensity light, and you see chemical reaction, there's a few questions that you really would like to be able to answer. One is, does localized surface plasmon resonance drive this chemical transformation? Meaning, as a function of wavelength, does this happen exactly at these conditions in which these nanoparticles are collecting that light energy? But even more importantly, is there this plasmon-induced charge transfer that I've mentioned before, where you have excited charges that are kind of scattering through this oxygen molecule, activating in that process? Or you really have the entire system of silver nanoparticles and this alumina that's being heated as a function of the interaction with light, and under the influence of this light, or of this heating, you're actually seeing a chemical transformation taking place. So we set out to try to answer some of these questions, and the first experiment is really simple. So here we're trying to understand whether these rates are higher under the condition of resonance when you're actually exciting these localized surface plasma resonance. And we use now optical filters to tune the photons that are hitting our sample, our reactor. And what we see is that when we excite this localized surface plasma resonance, we see actually chemical reaction taking place. And this is really not surprising. What it's really telling you is that the more light you extinct through this localized surface plasma resonance process, the higher reaction rate you're going to have. More energy you're using by the system, the higher reaction rate you're going to have. So this is really not that surprising. The second question of, is it different by energetic charges that are formed in this system, or it's really driven by thermal heating, is a much more challenging question to address. So we've done some experiments trying to answer this question, and one slate of experiments was to try to find chemical reactions that are taking place on this surface, on this system, but that are not excited, that cannot be activated by these electron transfer processes. So I show here now, again, the results of an oxidation process. This is now C oxidation, similar to that ethylene epoxidation that I've talked about earlier. And you see again, you run a thermal process, you see one rate, and then you shine light on. And again, this is a relatively low intensity, kind of solar intensity light, and you see the reaction rate goes way up. On the other hand, now you shift the gears and use exactly the same catalyst, but rather than running ethylene or C oxidation or ethylene oxidation, we're going to run ethylene hydrogenation. And what we see here is that you actually do not see enhancement in the reaction rate. If you saw the heating of the entire system, you would expect that this rate would go up as well under the influence of the thermal flux. However, what we see here is that under the light influence, the rate does not change. As you heat the sample, the rate goes up, but as you shine light of this intensity for identical catalyst, you do not see the rate going up. So this was kind of an indication that we might have something that has to do with these energetic electrons interacting with the adsorbates or with oxygen. Another slate of experiments is to perform kinetic isotope labeling studies. And it's been known all the way going back to Erdl and to some theory work is that the signature of the electron-driven reaction on a metal surface is that the kinetic isotope effect can be different or larger compared to the kinetic isotope effect experienced in a thermal process. So here what we do is we run a reaction of oxidation reaction, basically monitoring the rate of oxygen dissociation in a thermal process. We switch O16 to O218 and we monitor the reaction rate. When you make that switch, you go from a lighter isotope to a heavier isotope. So under thermal condition, using the transition state theory, you would expect certain change in the reaction rate. And we measure exactly what we expect, which is about 1.07 under these temperature conditions. On the other hand, if you have these electron-driven processes where electrons are scattering through these anti-bonding orbitals, you would expect kinetic isotope effect to be larger under the same conditions. So we do that measurement, again, the same experiment, oxygen 16, oxygen 18 switch, but we are now using it with light, and we see the kinetic isotope effect goes up to about 1.1 or 1.2 at low light intensity, for example, sunlight intensity. And then as we increase the light intensity, actually that kinetic isotope effect goes up further. So this difference in the kinetic isotope effect and this positive relationship between the light intensity and the kinetic isotope effect actually is a signature of an electron-driven process or hot charge-driven process on a metal surface, chemical process, as discovered by Erdl and others in 1980s and 1990s, working with these single crystal surfaces. So after we published this work, there has been a whole host of reports of what's been termed plasmonic chemistry. And what it means is that if you have a collection of these nanoparticles of silver or gold, and you shine light on them, under the light conditions, you are going to have different reaction rates and in some cases, different selectivity, meaning you're going to drive different reactions in different products, and you're going to drive them at the higher rates. And I show here some of the examples that have been published in literature. The question that we focused on is really trying to understand how does this energetic charge carrier, energetic electrons or energetic hole, end up in this anti-bonding orbital. And there's kind of two different mechanisms that one can think of. And one mechanism is the one in which is called indirect charge transfer mechanism. And this is a charge transfer mechanism that you would expect based on these extended single crystal surface studies. And the idea here is that, again, as I said before, you shine light, you create electron-hole pairs in the bulk. These electrons are colliding with each other, and basically you get something akin to electronic temperature. And then out of this distribution of electrons in this electronic temperature, you actually have electrons that are scattering through these orbitals. So this would mean that the closer the orbital is to the Fermi level, you would have more electrons at that energy, and therefore you would have more scattering for an orbital that's closer to the Fermi level. And you would kind of assume that this then selectivity in this process would be very similar to a thermal process, because thermal processes, again, go through these orbitals that are closer to the Fermi level in general. The one mechanism that we thought might play a role actually in this process is this direct charge transfer mechanism. And the idea here is that rather than exciting electrons in the bulk of this metal, because of these resonant interaction and because you're concentrating your energy of light close to the surface, very much at that interface between molecule that's absorbed and the nanoparticle surface itself, it would be possible to have direct excitation of electrons or this optical excitation at this interface of the molecule and the surface of the nanoparticle. And now the advantage or the difference between this mechanism and the other one that I proposed, the indirect one, would be that in this mechanism, you actually would have an opportunity to tune selectivity, because simply by tuning the resonance here, you can skip these orbitals that are closer to the Fermi level, and potentially you can excite the orbitals that are further than the Fermi level and then drive chemistry to those orbitals via this resonance charge transfer, resonant excitation of optical excitation at this interface. So to answer this question, we tried to, we used the model system where we basically covered the surface of these nanoparticles or these nanoparticles with dye molecules. And we use surface enhanced Raman spectroscopy using different surface lasers, different wavelengths, to monitor whether we can observe the signatures of the charge excitation at that interface or at the molecule. And I'm going to explain our results today by just focusing on metal and blue, but we have done a large number of these organic dyes that are interacting, that are deposited on the silver surface in many of these studies. And again, when you talk about a kind of signatures of this indirect charge transfer or direct charge transfer at the interface, one signature is that you would have higher anti-Stokes to Stokes ratio in this Raman measurement than the one predicted by Boltzmann distribution. So in other words, if I have an excitation of electron or a hole, and it goes through this anti-bonding or any orbital in this dye molecule that's sitting on the surface, because of the difference in the heat capacity, because between the nanoparticle and this molecule, I'd expect this molecule to get hot. And what that means is that because temperature goes up now in a Raman system, in a Raman measurement, I should see higher anti-Stokes compared to Stokes, because that's essentially a measure of the temperature of the system. So the question is, can I find systems and can I find the wavelengths at which this heating of the molecule that's not accompanied by the heating of the nanoparticle itself takes place? And another signature that's kind of associated with this first one is that as I increase the light intensity, there should be a positive or linear intensity dependence of this on this anti-Stokes to Stokes ratio. So the higher intensity of light I have, the more of these molecules would get excited, and I would see higher anti-Stokes. Basically, the molecules would be hotter. So these are now the Stokes and anti-Stokes Raman measurements. And again, I don't know that I explained this. Let me see if I have that slide. I don't. So the Raman can measure Stokes and anti-Stokes, as I said. And anti-Stokes are essentially a measurements in which you are probing the concentration of vibrationally excited states of a molecule, and Stokes scattering is you're probing the concentration of vibrationally not excited states of the molecule. So what we see here is that when we shine a laser of 532 on this metal and blue silver system, you see a very strong Stokes, meaning lots of molecules are vibrationally not excited, and you see a very weak anti-Stokes, meaning there's no heating of this molecule at 532 nanometers. On the other hand, now if you shine the same intensity, 785 nanometer, that's essentially less energy, same intensity, but you're putting less energy in the system, you actually see that your anti-Stokes is quite strong compared to the Stokes. So what this would suggest is that we have a very high anti-Stokes to Stokes ratio, 785, and this would indicate that 785, we might actually have a charge transfer taking place, or that excitation at the interface taking place, and 532, that's not happening. So we can even be more quantitative about this. So here I've basically selected a few vibrational modes of this metal and blue molecule, and we have measured anti-Stokes and Stokes and compared them to the Boltzmann distribution. And what you see at 532, basically the molecule is not heated. It's kind of sitting at the temperature of the nanoparticle itself. On the other hand, when you go to 785, you see that this ratio of anti-Stokes to Stokes versus Boltzmann is quite high, meaning that this molecule is getting hot. So what this is telling us that at 785, we have some condition that's causing this molecule to get hot. And at 532, even though we are shining more energy, we are putting more energy in the system, there's really no thermal heating of the molecule itself. We also monitored again how this anti-Stokes to Stokes ratio behaves as a function of photon flux, as a function of intensity. And what you see, there's this linear dependence where the more energy you put in system at 785, the more of this heating of this molecule you get. So this is again signature of charge transfer process to MB. So just to summarize this surface enhanced Raman spectroscopy measurements, so what we see is that there's an elevated anti-Stokes to Stokes ratio at 785, basically communicating to us that we have a non-thermalized vibrational population. We have a positive relationship between the anti-Stokes to Stokes ratio and laser intensity, again at 785 and not at 532. So what this is telling us that the charge transfer within the molecule, methylene blue molecule for 785 laser is observed in these measurements and not for 532 laser. Why do I use the molecular in 530 or 785? I don't. I mean, you still have them. They're maybe not as intense. Yeah, I don't know. So if this indirect mechanism was dominant, the rate of charge transfer should be greater for high energy laser, because simply we are putting more energy in the system. We would create high energy electrons, higher energy electrons, and you would expect that that electron distribution would be hotter, and therefore we would have more electrons that are scattering through this anti-bonding orbital and heating the molecule. And that's not actually what we see. We see that this lower energy laser, 785, actually induces this kind of heating of the molecule. So these experimental observations are contrary to the argument consistent with this direct charge transfer mechanism, and would point us in this direction of the indirect charge transfer mechanism, where you have some resonant process basically that's driving the excitation at the interface between methylene blue and silver, causing excitations through that methylene blue and therefore heating of methylene blue under these 785 lasers. So now corollary for this direct charge transfer is that it could imply a non-equilibrium heating of the molecule compared to the metal nanoparticle. So what this means is that if I have selectively, if I'm moving electrons selectively through this molecule, I can have conditions, I can have intensities of light where this molecule gets hot and the nanoparticle itself is not hot. So we can actually use this Raman spectroscopy to measure also at the same time the temperature of the nanoparticle itself by looking at the background of the anti-Stokes signal. So that's what we did here. And again, we are now measuring the temperature of the molecule, and we are measuring the temperature of the nanoparticle for these two lasers. And what we see is, again, that at 532, we have a thermal equilibrium between the nanoparticle and the molecule itself. So basically, the energy is propagating from nanoparticle to the molecule. Everything is in thermal equilibrium. And on the other hand, if we do this anti-Stokes to Stokes ratio to measure the temperature of the molecule itself under these conditions, and we do background of anti-Stokes to measure the temperature of the nanoparticle itself under the same conditions, we actually see situations where molecule is significantly higher temperature compared to the nanoparticle itself. So this is telling us that the energy is going through this low heat capacity molecule, and it's getting heated relative to the nanoparticle itself. So we kind of performed these studies for a large number of organic dye molecules, and we came up with a kind of a simple rules that tell us about when this direct charge transfer takes place. So you need to have high intensity fields that are driving this excitation process, and localized surface plasma resonance is giving you that. And then you have to have an electronic states that are available for that energy to go through that molecule or through that interface of the molecule and nanoparticle. And that means that you have electronic states that allow for fast electronic transitions that are driven by these fields. And in practical terms, it means that you have to have something that has a very large imaginary part of the electric function. So now if you marry that something with a plasmonic nanoparticle, you should be able to selectively drive energy into that something that has a larger imaginary part of the dielectric function. When you think about this, it's really not that surprising. You put energy in the system, and it's going to go down the path of low resistance, and that's provided by these electronic states that allow for fast optical excitations. So this kind of, like how this mechanism plays a role might not be that important. I mean, the electron ends up in this molecule or this entity that's attached to the nanoparticle, so who cares how it takes place? But it actually has a nice consequence, because actually it allows us to kind of build a framework for expanding this plasmonic catalysis beyond silver and gold. So what this is telling us now, as I said, if I have silver nanoparticle, I can get localized surface plasmon process resonance to collect energy that's interacting with this, interacting with light. And if I put now something that has a larger part of imaginary dielectric function than silver around this, that energy is preferentially going to be dissipated through that entity. So one model system that can be used to test that hypothesis is, for example, a silver nanoparticle that acts like an antenna covered with a very thin shell of, let's say, platinum. Now, platinum have this under UV visible light. It has these D to S transitions which are allowed in platinum. So you would expect that energy that's collected by silver to be preferentially dissipated through platinum through these D to S transitions. So we actually performed these experiments. It took us a very long time to fabricate a nice system where you have a large silver core and then cover it with a very thin shell of platinum. And here I show some of the elemental mapping of this silver platinum core shell particle. You can see here platinum nicely identified. Here you have silver core, and then you have a platinum on the edges of this nanoparticle. You can also do some high resolution transmission electron microscopy. So this is now silver. In this particular case, you see platinum here. You have 1, 2, 3, 4, 5, 6 layers of platinum. Basically, you have a little bit over one, between 1 and 2 nanometers of platinum that's deposited on a core of silver that's about 60, 70 nanometers in size. And this is, again, some of the elemental mapping that we did for these silver platinum core shell nanoparticles. And this is now how energy gets how these silver platinum nanoparticles respond to light. So this is now, again, silver platinum. You see the extinction spectrum of both. And now you can monitor using integrated sphere, you can monitor absorption versus scattering. In the case of silver, as I said before, when you have large nanoparticles, you expect most of it to be scattered into far field. And that's actually what's happening here. You see large fraction of this extinction is due to scattering. In the case of silver platinum, you actually see that you have much more absorption compared to pure silver, because again, you are introducing this this platinum, very small amount of platinum on the surface of the silver. We have also done some simulations, basically just looking at whether these simulations are kind of mapping out these experiments, and we see exactly the same situation. We see that scattering is much larger for pure silver. As we deposit a very thin shell of platinum, the absorption starts dominating this process. And we can use this modeling now to ask a question, okay, how much energy goes through platinum? How much absorption you have on platinum in these core shell systems compared to pure silver? And basically the bottom line is that as you deposit platinum on this surface, it exactly starts acting the way that I just described, where you have this antenna effect of silver, and then you have this platinum here, where most of that energy is dissipated through the platinum. So you get high field, you put platinum in, it has allowed electronic excitations, and then energy preferentially goes to that platinum, and you can get enhancements compared to having a pure platinum shell or having basically just silver. Since I'm kind of short for time, I'm going to quick. So then we ask a question, okay, if we can do this now we should be able to drive this plasmonic chemistry of this platinum, basically expanding the portfolio of the materials that we can use. So we used exactly this material now to perform a preferential CO oxidation in the presence of hydrogen. It's a very important commercial reaction. And we know that silver is a very poor catalyst for this process, it actually cannot do it. And on the other hand, platinum is widely used for this process. So the question is, can we now drive this reaction with this platinum-silver core shell nanoparticle, because it can happen only on okay, what's going on here now? Got stuck. Okay. Anyways, I have just a couple of slides somehow stuck, but essentially what the slides show is that this core shell nanoparticle of platinum silver actually can perform this plasmonic chemistry as we shine light. And what it basically telling us that this energy that's transferred to platinum is actually driving that preferential CO oxidation, and we see enhancements that are relatively significant. Yeah, I don't know why. And then my last slide was basically to talk a little bit about the field of this hybrid plasmonics, where we are kind of marrying this light harvesting potential of these silver or gold nanoparticles, and we're trying to marry it to other entities, be it a semiconductor or be it another metal or a dye molecule, where that energy is preferentially transferred to these molecules in the form of these electronic excitations, and then trying to use these electronic excitations for various applications. So with this, I'm gonna complete because my time is up anyways, and I'm sorry you didn't see the last couple of slides, but essentially I talked about chemistry on metals, the differences between electron versus thermally driven processes. I talk about these plasmonic nanoparticles, which concentrate energy of light at the surface as potential platform for some of these interesting chemical reactions that can take place under the influence of light. And I talk about silver as a metal that can actually perform these reactions. And I talked a little bit about the fundamental kind of underlying principles that are governing the flow of charge in this complex system where we're marrying silver plasmonic nanoparticle with other entities that can take advantage of this energy of light and drive electronic excitations in these other entities.
So you thank you very much, and never mind about these last couple of slides. I think this computer is part of the civil service, and right at the start of the lunch break, it went into freeze.
Yeah, that's true. Yeah,
that's my theory.
The labor.
We still have time for a few questions. Yes, please.
Thank you for your talk. I have a question about how do you actually get this thin film or thin layer of platinum on your nanoparticles in an even way?
Oh, that took forever. That was like my student actually fought it for like 3 years. So his PhD thesis was going to be a complete failure till he figured that one out. And I know some of you finish your PhD in 3 years. In the United States, we have 5 years. So I probably would have given him something else to do. But the idea is that you really have to find precursors of platinum that under electrochemical conditions can uniformly deposit on silver. And the one that we have commercially available, basically salts of platinum, don't have that properties. You have to really play with creating new precursors of platinum that would then allow for the really soft landing of that platinum and reduction under electrochemical conditions that allow for the covering of the entire surface. Yeah.
Yes, there's a question behind there.
Thank you for the talk. I have a general question about the simulations and the system that you've built with this platinum on foil. Is there interaction of these nanoparticles with the substrate relevant to these experiments, or is it not?
You mean with alumina?
So I think this example was silver on aluminum.
Yeah.
Yes.
So it's alumina. So the idea is that we have a support that provides mechanical framework for these nanoparticles to land, and that would otherwise be inactive optically or chemically.
Right, but the field simulations you showed, they showed particles suspended, and I just wanted to ask about whether interaction with the substrate is relevant to the plasmonics.
So we did our simulations for those on alumina as well. What I showed here was the suspended in the nanoparticle. It complicates optical response a little bit, but nothing that would change the story.
Thank you.
Hi. So many thanks for the talk. It was very inspiring. And I have a quick question. Have you tried to achieve the same antenna effect with cheaper plasmonic metals such as copper?
So the fundamental problem that I think kind of comes into play here is that I think if you want to achieve the antenna effect, from my perspective, silver is the best option. Because simply it's the least loosey material. So you can transfer most of that energy to another material. All these other materials like gold or copper are going to actually induce lower fields than silver, and therefore the efficiency of that transfer is going to be lower. So I think that, and you know, from a perspective of cost, I mean, silver is not that expensive. I mean, compared to platinum or something like that, it's just not.
Thank you for the answer.
Great. Do I see?
Yeah, thanks really a lot. So I have a brief question, maybe like a broad question. So what do you think it's necessary to transfer like photocatalysis into the industrial scale? Because currently it's like mostly thermal, right? Like 90%, 95, 99. It's all like really extensive use of energy. So what do we need to transfer like this kind of technology to like industrial scale?
So I think there's really a number of problems that one has to address before this is transferred into kind of commercial application. I'm going to speak broadly, not just about plasmonic, but also semiconductor, catalysis, for example, photoelectrochemical splitting of water to create solar hydrogen and stuff like that. The first thing is we really have to develop reactors that allow for high penetration of light that don't have wasted volume. So we know that the characteristic length for light penetration is not very high. And therefore you have to have reactors that are designed so that they can take advantage of that fact, or that they have to account for that fact. When it comes to, so reactor design, it's an engineering issue, but it's a big problem. The other issue is many of these processes, the reason why you would like to use light is because you are driving an inherently endothermic process, for example, water splitting to pour hydrogen, or CO2 reduction to pour fuels or chemicals. And these endothermic processes are characterized by the fact that the chemicals want to recombine and go back in the initial state. So separating your products as they're formed, for example, in the case of solar water splitting to form hydrogen and oxygen, you have to separate that hydrogen and oxygen. So being able to separate them is another critical thing. And when you talk about this, then you start thinking about, well, do we need, for example, a multi-component, multifunctional systems that can kind of separate, run reactions separate at the same time, and then all of these, you know, kind of questions are where this field is going are emerging. And I think solutions are going to be reactor design, a big one, and then bringing more functionalities to the photocatalyst, kind of the second big one.
Good. I see hungry silence. So let's thank all the three speakers of this morning once again.